because the whole Tsys measurement, and then I go and I did the radiometer equation yesterday, and which uses the Tsys measurement and with the radiometer equation. So I think the whole Tsys thing was really fun and sort of exciting to measure. And Preston, you just said you measured your Tsys. What'd you get?
Okay, I got 779, which to me is a lot higher. I think it's because maybe I can't see above 40 degrees in declination, so I couldn't go up to the real cold area in the sky.
Okay. Well, this is, I think, important because you know sort of what your limits are. Okay, Alex, go ahead and we'll learn more about Tsys measurements.
Okay, here goes. Woof woof. Let me see something here. Share screen. Okay, I'm not gonna. I put together like a presentation, assuming no one knew what this stuff. But
there you go.
Okay. Anyhow, without belaboring the point, the Y factor is the power ratios between hot and cold. And typically it's hot environment 290K and cold sky. And in addition to that, what you're also measuring is the added factor of the system noise is contained within both of these levels. So typically it's measuring warm earth to cold sky. And this is kind of the idea, is you measure two values and it's offset. It doesn't come to zero because you have another component which is related to the system temperature. Anyhow, this is one of the combinations. And so with this system, I can really point it down, and I did this at several locations in the yard. I have heavy vegetation, so I can definitely grab hold of 290K and then point it up, and I have some clear sky overhead. This one shows a difference of really about 7 dB, but I did another calculation where it was like 6.4. I come up with a Tsys of 73. And then I came up with another idea. Why not try Tsys measurements between two hydrogen brightness levels? Let me see how this goes. Oops. So there is this online calculator that I think Wolfgang pointed me to months ago, and you can put in the parameters of your antenna, the beam width, and locate any point in the sky, and it will give you the effective Kelvin temperature. So this was the brightest part in Cygnus that I measured above cold sky, above the background. It's like 2.7 dB, and it corresponded to 57K. And then I went over to that other area was very cold at 12 hours, same 40-degree declination, and got this. Not much of a signal, but it's only 1.4K above the background. So I just did, I didn't try to do much with this because the numbers are so small. I just put this sloping line here that says this is 0, so it's about 0.06 dB above the background. If I use those two numbers, 0.06 and 57, come up with this figure, I come up with 65K. And there's even a third variation on this. So the Earth and sky got 73 using these H1 levels of 1.4K and 57, I got 65. And then I just came up with another level, another combination. Okay, what if we offset this by the nominal 10K cold sky that's typically used over here, come up with 56. So I got 56, 65, and 75. 55, 65, and 75. and they're all very low. Wolfgang did an analysis of the data that I acquired at the S7 region, and he came up with 120K. But I don't know why these numbers are so low. I will show you something. This is what the system looks like. The feed is pretty well deep in the dish. This is about a 0.2627 F to D ratio, so it's well shielded from ground. That's what the surrounding area looks like around my house for the 290, and there is some clear spot overhead. I don't know. Comments?
Okay, I will try to comment that quickly a bit. Your first measurement, which is the hot-cold, looking at the bushes, which are a pretty good, most likely a pretty good black body radiator, and the sky position, I think that should give you a good number. So your system temperature determined by this method is fairly low, so it's very, very good. But then if you look at your setup, because of a very well shielded feed and maybe not a full illumination of the dish, it doesn't seem so out of the world. I mean, it's still in the realm of possibilities. The only puzzle for me is that if I look at your S7 data, I find a substantially higher noise than expected from that. And quite frankly, I don't have an explanation for that. There is, in both cases, you have an uncertainty. What I think might be one of the reasons is because you have a fairly wide beam width, the extrapolation of what is the peak brightness temperature of the S7 might not be accurate enough, or might be off. And what I'm trying to do, and I've discussed that with people, what we will try is to make a new analysis based on more recent survey data. There's a very detailed survey data which is available, and I talked to the people who did the survey. And what we're trying to do is, I mean, the idea is essentially to come up with a number of figures saying if your beam width is such and such, you would expect a peak brightness temperature of so and so, and so on, and go for very large dishes, or sorry, for very large beam width, which I may resolve the problem.
Okay.
Or so I'm working with that. It will take a while because I'm talking to one of the prime authors of the survey, and he's dealing with that. The other point on your second type of measurement, maybe if you can share your screen again, please, and show that.
And by the way, Alex, didn't you use a resistor also?
Yes, okay, all right, here's something else. So this is just a rough comparison between the wooded area shown in the picture, and I did it 10 different times, came up with like 52.5. The cal cover with the foam is 53, and the 50 ohm resistor is 50.5. So they vary a little bit, but they're, you know, in the ballpark. Let me see, Wolfgang.
Yeah, I guess that's the one.
This one?
Yep.
Okay.
Now, I still want to have a look at more detail, but I think there is an issue with that, because when you are, let's say if you go on the hot side at 57 Kelvin, you have a brightness temperature of 57 Kelvin from the hydrogen, but you do not know what is the background behind that, because you will have a continuum background. You're looking into the plane of the galactic plane, so you have an additional radiation coming in there. So you have the 57 Kelvin, but you have another background, which is some unknown number. And then you compare it to another region where you again have a different background. You cannot assume that it is 10K background in both cases.
Then how do you do can you even then does is this measurement even valid? Me just picking this is pointed up. In other words, let's say looking at this, I assume that this level would be 10K in doing the very initial calculations like this. Maybe this is bogus.
The assumption that if you're looking at the cold sky at a location, let's say close to the galactic, to the celestial pole, there's a safe assumption that it is 10K. But if you go to a different position, like in the galactic plane, it is no longer 10K as the background.
Okay, well, see, I have a record of that, and I took logs. I didn't see that changing more than, I don't know, half dB or something like that. Just last week, I took 48 hours worth of data, 2 different scans, 24 hours, and over that 24-hour period, I didn't see a huge change in the level of the background. It didn't change that much over time. But okay, I mean, you're giving some ideas. Yeah. And the only thing I'm trying to say here is it's not necessarily a straightforward method.
Yeah, I mean, the real straightforward method is the first one that you use. I'm looking at an area which is essentially has a brightness temperature of some 270 or 300 Kelvin. That's okay. That's okay. Probably very good, fair enough. And from all the measurements that I did, looking at bushes like you do, that's a fairly good black body radiator. So okay, that's okay. Looking up at the sky, if you're at the cold position like the celestial pole, that should give you something like 10K. There was a comment by Marcus Leach who said, well, maybe it's more like 4K, but that wouldn't make so much of a difference anyway.
And see, I can't get there because I'm in the bushes. And so as someone else said, they couldn't get to the NCP because of their limitations. That's what it would be nice to come up with an idea of how this method could be used, because you don't have to relocate the telescope. You could stay at one declination. You just let 10, 12 hours pass and you get 2 points. So it would be interesting if this type of technique could be used also to determine the Tsys.
Well, very much depends on actually whether you, what the background radiation is, if the level shift that you get. I don't have a number for that, would require further investigation.
What the problem? I'm sorry. What the problem with that, Alex, is that you might be in the daylight on one observation and the darkness in the other, and it's just the temperature differences on all your equipment.
I don't see a change. I ran a temperature characterization of the LNA a couple last week. Put it in a little oven that I made, ran it from 75 to 120 degrees Fahrenheit, 1/10 of a degree dB change. Basically, it's stable. I've been trying to do some system characterizations to say, is there something strange about my electronics, and I don't see it. Something else like I use the WD5AGO LNA, which has a 0.28 noise factor or something like that. I just stuck the little Sawbird H1 with a 50 ohm resistor in it as a noise source, and I think I had to add 10, 11 dB in series that I could put in step attenuators, and that it would cover the same range in the SDR. And so this was adding some different physical attenuators into the SDR over the same range of analysis that I was using for the sky measurement. So I can at least say the SDR is linear, that there's nothing wrong with that setup. So I've been trying to come up with some ideas of seeing if I could find a source for this disparity.
I mean, the only disparity that we actually have is that the S7 measurement indicates a higher higher Tsys. I don't see any problem with your measurement, the hot cold. I mean, it's
Okay.
the number that
Okay.
73 Kelvin is a very low number, a very favorable number. I was skeptical in the beginning, especially because the S7 did something different. But I have to say that the way your design is, with the way of the shielding of the feet, which is essentially almost completely shielded, that will tell you that you most likely do not have much of a spillover.
And I also added aluminum screening in here because those slots did allow some ground noise to come through.
Yeah.
So the bottom end dropped about another dB by me adding screening over this.
And the other thing is, the other contributing factor is the LNA. You have very good LNA. It's a fairly low noise one. So the ingredients are there. Your hot cold measurement indicate a low system temperature. So that looks quite plausible to me.
Okay.
The remaining question is why is the S7 measurement then different? And I think from all that I can think of, it is something that the extrapolation of the data to fairly large beam width may no longer be accurate enough. And I'm hoping to get some insight into that in the next couple of weeks.
Do you think that profile generator is giving me valid numbers for 20-degree beam width?
Yeah, that's why I, in the meantime, put a bit of a question mark behind.
Yeah.
So what they're doing, they're using the survey data and then doing a integration over a certain area. And the attempt that we are now doing is we will use more recent survey data, which is also higher resolution, and then integrate and using different beam sizes and see what is a brightness temperature that we do see with that.
It'd be interesting to see if we could come up with something that's a little more consistent.
Yeah,
but
I mean, on the other side, if I look at the data that we are taking with our telescopes, there the systems, the Tsys measurement using S7 and using hot cold is fairly consistent. But then, having said that, we have a smaller beam width. Typically, we have 5 degrees or less. So that's we're in a different ballpark as far as extrapolation is concerned. And I think at this point in time, I would suggest we put it at rest until we have more or have either better data for the S7 extrapolation, or we find that the new data gives the same extrapolation. Then we have to revisit where does the difference come from.
So let me ask, and I'm going to bring Preston on right after this thing. For our group, our amateur group, the best approach to measure their Tsys, get a baseline, probably just a reproducible baseline that they can hang their hat on. And so when they make improvements, they can show an improvement with a Tsys measurement. And I'm thinking that, does your 50 ohm resistor, would that be the thing you would use to, I mean, get a consistent T hot measurement? Or would you go ahead and still use the sky or the ground noise?
Well, the resistor measurement doesn't tell you anything about your antenna. That's where part of the noise comes from. It is just showing you the characteristics of the electronics, and any change and any optimization of your feed characteristics and the beam illumination, and so would not be visible there. So really, if you have a chance, given your environment, if you can do a hot cold using bushes, or even ideally have an absorber and then go to a cold sky position, is probably the best that you can do for smaller beam width, like let's say for a 3-meter dish. It seems that the S7 method is quite reliable. Then when it comes to improving your system, you are not so much dependent on making really an absolute measurement. So what you want to know is, am I getting better compared to the previous one? So you could still use, even with a large beam, you could use S7, and even though the absolute number may be not that accurate, you can still see the improvement if you have done an improvement. So for that purpose, it should work.
And I ask, is it fair to say that since you're dealing with the changes in beam width, that if you make an error or have errors in understanding that the differences between your reading and other readings could be a square function and so forth, changing at a fast rate and not just a linear difference? So errors can magnify faster.
Well, the whole idea behind the S7 calibration region is that there is a region in the sky which is inverted comma fairly large, which has a uniform brightness temperature. Now, this is valid for 0.5, 0.6, maybe up to 1 degree beam width. But then as you get larger, you are encompassing an area which is much bigger, and there are temperature variations occur. So it's no longer uniform. And how much does that change? It really depends on what is the structure of the hydrogen in that region. And as I said, it's probably, to put that on a firm ground, is really to revisit this extrapolation. I mean, the S7 originally was intended for telescopes which have a fairly small beam width. For example, for our 25-meter dish, it's completely uniform, and that's an easy thing. The advantage of the S7 compared to the other methods is so fast. I mean, you just take one spectrum and take out the pocket calculator, and you're done. That makes it very convenient, other than going to different positions and having two measurements. But at the moment, I see some signs that for large beam width, like 20 degrees and in that ballpark, the method may not be suitable enough, or maybe not accurate enough. At least that's a certain suspicion, and we have to look into that.
So why can't we?
In the North Pole, the whole idea of the S7 is really that you have a defined brightness temperature over a certain area, which at the celestial pole you don't necessarily have, especially not for hydrogen.
So it's not hot and it's not cold. It's a medium number. Okay, thank you.
Preston, you've got your panel here that is going to go over your measurements and give you some advice on how to go from 779 Tsys and try to beat Alex's antenna system to get down to 50. So why don't you explain what you did and your antenna system, and let's see if we can give you some advice.
Okay. Can you hear me all right?
Yep.
Okay. Excuse me. I got from Amazon, I guess, I ordered some absorber, and it's, I don't know, just, it's not real thick, maybe a ½ inch. And I used 2 layers of that. And I couldn't find a plastic dish that fit over my feed. So put it in a plastic bag and pulled it back and taped it tightly. So the whole feed was covered. I don't know if it's thick enough or not, but that was my hot reference. And then for the cold reference, I went as high in the sky as I could go, which was about 40 degrees declination. And it was 90 degrees in elevation. So I went up there to get my cold reference, and I think that's where the problem was, because I think I might have still had a piece of the main plane of the galaxy there. Anyway, I've got the radio astronomy supplies receiver, and it reads out in volts. It reads from 0 to 10 volts. So what I did with the hot reference was Oh, and there, as you know, there are many adjustments. There's a gain adjustment. There's also a voltage offset adjustment. So with the hot reference, I set it about center screen with the gain. It was about at 5.1 volts. I set the gain for that. So I was center screen. And then my offset was 1 volt. And then my offset was 3 volts for the hot. So then I went to what I hoped would be cold, and the offset for it was 1 volt. So it's a difference of 2 volts. But when I add that back to the 5.1, I get 6.1 volts and 8.1 volts. Well, that ratio is not going to bring a very good Tsys. So I'm assuming that I can use the voltages that way. Do I need to square them or something? And the other thing is, maybe I need to find a period of time when I can catch one of the gaps in the hydrogen and use it for a cold reference as it goes by. So did I do right what I did, and do I just need to find a better reference, or should I have squared my voltages or something?
Let me ask you a couple questions, because I got a Spectre Cyber here in front of me too.
Okay.
Were you in total power or in spectrum mode?
Spectrum mode.
Okay, I'm not sure spectrum mode's the right one to use for this measurement. And because it's doing a narrow band sampling spectrum as opposed to total power. And I'll ask you guys too about that. Is that I'm thinking that is one of the issues on what he did, because I don't think that the ratio, the offset thing is an issue. I don't think that's, I think that's still good. I think it's just this being in spectrum instead of total power mode.
Yeah, my bandwidth would have been 5 kilohertz.
Preston, did you measure the conductivity of that material? Did you stick an ohmmeter across it?
I did not.
Try that. Make sure it's actually conductive material, because I bought some. In fact, I'm trying to figure where I bought this from. I bought a stack of it from an electronics place. I think it was Newark, but I need to find out. It was less expensive, but take an ohmmeter reading across it. It should be just about 0 ohms. So that may be a problem. Check the conductivity.
That could be. I will do that. In fact, when I'm not talking here, I'll do that and come back, and I'll type it up in the chat. Okay.
Anybody else have any recommendation? What'd you use on T-cold? So you just went to the 90 degrees up from your latitude, right? And
Right.
You can't flip it around and look at the celestial pole?
No.
Okay. Let me see what else. And what size of a dish you got?
12 foot.
A what?
12 feet.
Oh, you do? Wow. LNA?
It's 0.28 or 0.3. I can't remember. It came from Radio Astronomy Supplies as well.
That's
Okay.
the same one that I use. Yeah.
How much cable you got?
I'm Tom Henderson.
I got a lot of cable. I got 80 feet of LM500.
And your receiver at the end? Oh, it's a Spectre Cyber. Never mind.
Yeah.
Okay.
Yeah.
Does it matter that he's down converting to an IF, an IM?
I'm not, mine doesn't down convert.
You're at 1420 all the way over? The Spectre
Yeah.
Cyber is down convert.
This was, if you remember, I don't know if you were there or not. A few years ago, it was given away as a door prize, and it's completely self-contained. It was a lab model. It wasn't the one that sold. So if a down converts is doing it totally internally, it's just one box and you put 1420 into it.
Okay. Any other recommendations on improving his system to, so it sounds like it's a measurement. We think it's a measurement problem up front, potentially on your Tsys measurement, and unknown whether you can improve your actual antenna system until you get that Tsys measurement worked out.
Okay.
Is that what I'm hearing?
Preston, what feed do you use on your dish?
It's a radio astronomy supplies feed.
So it's kind of a Kumar feed, so it's a waveguide, circular waveguide with a choke ring around it, correct?
Yeah, it's well, I couldn't get the choke ring on it, so it's running without the choke ring. The way my dish, the angle that the braces come up there, it would not fit on there. So,
well, in any case, I think the indication is that there's something with the measurement rather than with the system itself, because a almost 800 Kelvin system temperature is way too high, in particular because you do have a good LNA, and unless it's broken, it should deliver good results for a 12-foot dish.
and I also put up some curves for y'all one time, and they were great, you know. So they were like 7 or 8 volts tall, the curves above the background. So
Would the feed at the wrong focal point cause the Tsys to go bad? I mean, is that something you could check?
Not that bad.
Not that bad. All right. All right.
Okay.
So next month you're going to give us some feedback on your new measurements, huh?
Okay. I
That's great.
will go down and see if that absorber's any good now, and be
All
right. And I'll put it in chat, so I won't interrupt what's going on at that time.
Great. Thanks.
You're welcome. Thank y'all.
And now anybody else got any more of this? And then I'm going to turn it over to Jay and Ted. We're going to sort of give a walkthrough of the Little Thompson Observatory main area there. So anybody else did a Tsys measurement? I don't hear anybody. So you guys want to, 10J, you want to try to do a walk around of that room there?
Sounds great. We sound different. We look different. I moved this time and everything like that. Because we're over here at the Little Thompson Observatory. Later on today, we're going to have a group of STEM students come in preparing for the next year, this summer coming up. And so here we are to meet them. We're in a big room here. It's about 60 by 30 feet. And Jay and I are looking at a great big projection screen where we have presentations and speakers come in and educate the community, as well as all the volunteers that are helping out. We're actually on the high school grounds here in Berthoud, Colorado, about an hour north of Denver. But we are an independent group from the school itself, from the school system, which works out really well. Jay, what is it? We pay a whole bunch of money. What, every 10 years?
Yes, every 10 years we have a $1 lease.
So that's negotiation. That's good. So the big screen all around the room. Of course, we got lots of posters for education, and we think that's just great. Yeah, excellent. And boy, do we have chairs. Room enough for 50 folks. They could be short and tall. It all works out very well. There are a bunch of birthday parties that come in here, celebrations. That's a really nice floor we have there. And, oh yeah, that's better. Lots of pictures, including many from the days of photography and film from one of our high school impressive science teachers, who goes off in dark places and took wonderful pictures for us. So we think that's pretty exciting. Many folks could be in here, which works out just fine. But we often look at the star wall here and give a talk. Someone will stand up there and kind of dance and point and things. We talk about constellations. Pisces here and down here, we talk about where the ecliptic is, how the galactic plane fits into all this. And then we were doing a test before, we can't quite show you. We turn off the lights above and turn on the black light onto the screen, and then things glow up. I consider that the test. Can you remember where the constellations are if you're given just the dots? Now, Jay, you're going to talk about a different part of the wall. I'll push buttons.
Yes, the portion of the star map that Ted was in front of is, of course, based on our traditional view of the sky. And the way it is set up is the spring equinox is on the left side, and it's repeated again on the right side. So we can sort of talk about the apparent motion of stars through the seasons. And the one thing that is failing on that is would be on any printed map is the location of the sun and the planets, and the moon. Just this week, Ted and I have obtained a couple of video or computer projectors, and we hope we'll be able to do an overlay over our painted star map, so we can show at least the semi-current location of the planets, because we get a lot of questions about that. So what Ted is panning,
Let me go back then.
what Ted is panning across now is a very important graph for us. This is the sky as viewed by the Lakota people of the North Central Plains. Now, the Lakota people were different from most native tribes in that they made a written star map, which is believed to be about 2,000 years old, or perhaps a little older, because of the way they positioned some stars in the sky, and our precession has, as well as possible movements of the stars over 3,000 years, has caused a discernible movement from their original star maps. Their star maps were drawn on the inside of buffalo hide, and they used those maps as a basis for a treaty in 1868 with the US government, giving them lands. A part of their very deeply held belief is that everything that is in the sky is on the earth, and everything on the earth is in the sky. So as a result, they have drawn maps of a nomadic pattern, in other words, a migratory pattern on the earth that they would follow based on this thing you see in the sky, which is called the Great Racetrack. That goes around many of the constellations that we would identify, but they saw them differently. That white band in the middle is actually what we would call the Milky Way, but they call that the road of the spirits. And they use the cardinal points around that racetrack to help guide them on their annual migrations. And it was quite helpful. It allowed the migratory group or the nomadic group to be in the location where prey could be captured, generally buffalo and other large animals. They would then be in another place when it was a good time to pick food with spring crops. And so according to tribal tradition, about we would say 3,000 years, 2,000 to 3,000 years. They would say since the beginning of time, they followed this pattern. The sad part of this is the Treaty of 1868 was pretty much abrogated by the US government. That resulted in what we call the Battle of Little Bighorn, where Custer and his men fought an assembly of tribes, and the US Army lost that battle, the Battle of Little Bighorn. That was an attempt on the part of several tribes in North Central Plains to reclaim lands that had been promised to them by the Treaty of 1868. Now, why do we have this map on our wall? Well, one of the things we wanted to do in the observatory was to educate our visitors to the fact that there are indeed different ways of drawing constellations, different ways of interpreting what's seen in the sky, and not just from a spiritual, cultural perspective, but also from a practical perspective. You know, here, these were what Western folks would call primitive people, had a very sophisticated system of astronomy that allowed them to do something very, very practical. And that was to live off the land for thousands of years with very little assistance from the outside. Now, the tribes, of course, would trade among one another, but many of them were migratory, as the Lakota were. The inspiration for us to use the Lakota map was simply accessibility. They were kind enough to let us look at their ancient maps, take photographs of them and drawings. We worked with many of the elders from the Rosebud tribe in South Dakota. It's near the city of Rapid City. And they had an astronomy department that had been established at their community college. So we worked very closely with them to get this map drawn as accurately as possible. And it's updated as things change. One of the landmarks on the Earth portion of this map had previously been known as Harney Peak, a very significant piece of geography. Harney Peak, you can walk up it in about 10 minutes. It's not a very high rise from a parking lot or even at the river level around. Most people in the world have never heard of Harney Peak, but this is the highest point of land between the peaks of the Rocky Mountains in North America and the Pyrenees. It is just absolutely stunning that there would be such a thing just rising up in South Dakota. Harney Peak was named after a US Army general who did not really do right for the native peoples. And so it's been a point of contention for many, many years, nearly, well over a century and a half, that this landmark would have been named by the US government for somebody who was quite offensive to tribal people. That peak was officially renamed about 4 years ago, Black Elk Peak, in honor of one of the tribal chiefs from that period. The official renaming of that peak was done in this observatory on this star wall. We had a large number of tribal elders, a ceremony, and in fact, one of the descendants from General Harney was here to help us remove the old label from our wall and add the new label. So we have a close association now with the Rosebud, the tribal headquarters on the Rosebud Reservation, as well as the community college there. If anybody is interested in researching a little bit more about this, there is a book available on Amazon, published by the Tribal College. The name of the book is Lakota Star Knowledge. It's written by a Goodman is the name of the author. And if you don't want to buy the book, if anybody would like to contact either Ted or me, we will send you a PDF of the artwork that we use to create this star wall. So any comments or questions? Love to have you come visit.
If you give a tour, you might have to know the constellations in the Roman way, but we have to know the constellations in the Indian way too. So that's kind of exciting. There are different dots in the sky drawn, connected differently. Now, of course, along with this, we have telescopes, all kinds of stuff outside, Jay. We even have a 6-inch upstairs in the dome, connected to a 8-inch telescope upstairs in the dome, and another dome with a 24-inch telescope. So we're proud of those, and we think that's just great fun to have tours. In addition, the 15 and 16 you've often seen behind my ears, the 15 and 16-foot radio telescopes are outside, out behind this star wall. We got a weather station. We have radio Jove antenna pointing up in the sky, and we study the meteors at about 6 meters. So try to incite excitement in science at all kinds of entry points. That's the quick tour. Come and see us. What are we? Starkids.org.
Yes, www.starkids.org.
Check us out. Anyway, a remarkable facility here. Dave, you're on camera.
Yeah,
Another SARA member has just arrived.
I think I paid my dues.
Well, otherwise we'll cut you out of this.
Yeah.
Thank you, folks. Back to Rich.
Well, thanks, everybody. Anybody have any questions for them? It's a great facility. I've been there a couple times, and Ted gave my grandkids a tour of even the downstairs, the underneath, which they loved. Okay, let's see who else is online here. Wolfgang, you got anything else going on from Osterpeeler?
Yeah, maybe I can show a few photos. Let me. Okay, can you see that?
Yeah.
Okay. This is the, let's call it the latest addition to the collection of dishes that we are working with. That is not on our site. That's on the rooftop of the Argelander Institute, which is the astronomical institute of the University of Bonn. And we just a few days ago had first light with this one. It's a 3.2 meter dish. And this is, it used to be one of those SRTs, which we completely refurbished, and it has a new electronics for the motion and also the complete new receiving chain. And this will be used for lab courses at the university. And essentially our role was that we transferred the design of our small dishes to this one. There were a couple of students helping along with building that and building the electronics. So this is something that we've been working on for the last couple of months. Essentially, maybe I show a few more. Let me see, how do I get that? A few more photos. Yeah. There's something which you may note, or maybe one more, that the feed horn seems fairly long, unusually long for a 21 centimeter feed horn. The background of that is because it's in a rooftop in a down to essentially a urban area, we were concerned about interference from essentially mobile systems. And by that fairly long feed horn, we make the cutoff at the lower frequencies very sharp and very deep. So it suppresses GSM, for example, very well, the 800 megahertz range. And we had previously done some test measurements on the roof and see what was the RFI situation. And it turned out that by using a long feed horn, this could be very well suppressed. So it's just the very beginning. We set it up, did some test measurements. By the way, the system temperature of that is 100 K. So that's what first thing that we measured. Yeah, that's sort of the latest thing that we did.
Wolfgang,
Any questions?
yeah, this is Jack, Wolfgang. The straps that are on the mount, was that because you were getting some flexibility or wind movement or something? Or
Yes,
what was?
exactly. That's we're going to replace that by a more rigid construction, but we found that there was a bit of vibration and movement of the vertical pole, and we wanted to reduce that.
Right. Okay, great.
Wolfgang, I think it might be useful to document what you did for that feed, because people are going to be installing antennas in high RFI environments. I got by with the standard SETI feed, which was, I don't know what, 10 inches long, but knowing what those parameters are might be useful to other people that are having Wi-Fi issues.
Yeah, it's essentially a SETI design. It was just a longer waveguide.
Roughly how long?
60 centimeter, I think. It's not very critical. It could be 55 or something in that ballpark. It's just that we found that we get a very deep suppression of the 800 megahertz mobile band by using a longer feed.
This is Dave at LTO. Terry and I had tried a similar approach, but we did not make that cylinder long enough. We have a very bad interference problem here. And we went to a cylindrical feed, trying to get rid of that. We would appreciate your information on the length and the makeup of that feed.
Yeah, I can certainly share that. Maybe the best way to do that, to put it on listserv.
Yeah. The other thing you mentioned was that the SETI calculator does not estimate that choke ring precisely. Any more information on that, and how you adjusted it to sort of compensate for the calculator?
Yeah, the finding was that the position of the choke ring, the position along the axis of the feed horn. There's let's say a number that's given by the SETI spreadsheet, and we typically, what we do is we put the feed horn on a we measure the beam characteristics of the feed horn essentially by rotating it. That's a separate setup, and then we just adjust it to what we think is best, and matching the dish. By the way, this is a 0.4 F to D ratio dish. So it's really a measurement rather than any calculation. So we just go and measure it.
Okay. All right. Any more questions for Wolfgang? Any more FRBs or magnetars that you found lately?
Magnetars, the one magnetar that we are observing frequently, which had a period where it emitted fairly strong pulses, single pulses, that we could detect as single pulses. This seems to have entered a different phase now. What we find is that we do see it. We get an integrated profile like from any pulsar, but we don't see any, well, only few very large pulses. So it's now in a different state again. There were periods of time when we had many, like 100 per hour, very strong single pulses. And now it has turned to a different, where you still have a clearly identifiable signal, but not many single pulses. So we'll continue to observe that. On the FRB front, we just started a new observation because we had some reports from the CHIME telescope that one of the repeating FRBs may be active again. So we were just started 2 days ago, we started observations, but we haven't seen anything yet.
All right, thanks. Don, are you there? Got anything going on? Anyway, DSES, Deep Space Exploration Society, which is the people who are in Colorado Springs, basically, and the facilities in Haswell, Colorado, which is east between Colorado Springs and Pueblo, are just got a grant to put in a building. We're gonna try to get in a building pretty much I think the main room is about the size of the Little Thompson just showed. And so they'll be able to have that. They'll have a control room that's looking at the antenna. They'll have a bunkhouse, a bathroom, various other things. So they're turning it into we got one trailer that's dusty all the time to something that's a little more formal, and they're even going to pave the road a little bit. So we're getting into the 1800s as opposed to the 1700s, era. So anyway, anybody wants to come down there, just let us know. They just recently ranked 7th on the EME contest with ARLL with that dish. They're one of the big boys in the block now for the world with a 60-foot dish. So that's working out well. Listen, they're currently, and Dan Lane's currently trying to build a feed or get a feed built for masers. And so that's the next sort of goal for the club is to go into the maser realm. They've also got 2 3-meter dishes that they're going to try to do interferometry with, and they've got one of the dishes put together. They're looking at the other one now, and they got a full ham suite. I mean, every frequency and you can think of. So, all right. And I'd say that because Don's on the board, so I was going to sort of give a brief for him. Let's see. Johnny Cox, yep. I think you're new. Oh, wait, Don, is that you?
Yeah.
Oh, okay. I was wondering if you had anything else going on.
I did just pick up thing here called a Pluto Plus, which is like the analog devices Pluto, but it has a built-in a built-in a web internet socket, and we'll take a one of the accurate clocks that you can put in, so you can use either an internal or external clock, and it has 2 channels of transmit and 2 channels of receive. I'm going to exercise it. It's not a bad deal. Made in the old country. We got to buy that stuff before we go to war, because we won't be able to get it after that.
We need to find old country. I'm lost at which old country we're talking about.
Oh, China.
Oh, China. Okay.
It's a joke.
All right.
Made in the old country.
I was going to say England, but that's a different old
it used
country.
to be Germany.
Yeah, or Germany. Yeah, one of the two. All right. Okay. Thanks, Don. Let's see. Next on the list is Helen. You got anything going on?
No, we've been out of the country the last 3 weeks. So, in fact, we're just back this weekend. So, but I didn't want to miss another presentation. So thank you.
Glad to have you back.
Thank you.
Let's see. Bob, anything else you want to go over?
No, I'm all set here. I enjoyed the presentation of the observatory and the discussion about the old tribes. That was very interesting. Thank you very much for taking the time to go through all that, guys. Back to you.
All right. And now they can run conferences and build software and discuss ancient tribe astronomy. This is really a good group down there. Jack.
Yeah, I'm at the moment I've just completed the design and the building of a new position encoder system for my antenna. I'm going to turn that into an article and put it on the journal. But basically, it's allowing a lot higher resolution incremental encoders, and it contains trim encoders and readouts and all that kind of stuff. Plus, it's web connected, so you can hook it up to things like radio eyes and other things to show position, and it also hooks into my position control system too. So anyway, when I now that it's finished, I'm just running it through a lot of tests, and I'll probably try to stick it in the journal here in the next couple of months.
All right, excellent, thanks. Mike Simpson.
Well, I'm just basically just glad to get back on and listen and find out about what's going on with the club. And I haven't done anything in a while, but now that it's getting warm in Utah, I can unpack stuff and clean up some stuff. Let's see, but that's pretty much it until, let's see, next year I'm going to be moving to the Philippines. So I am very interested in noise reduction, since just about everyone has a cell phone, and I'm going to be living close to the beach, but you have a lot of noise. So I'm just trying to get everything ready for shipment over there. But that's pretty much it. But it's good hearing from everyone and seeing everyone. I appreciate it. Thank you.
Hey, well, thanks. And yeah, I was in Olongapo for a couple tours. Well, not tours, but visits when I was in the Navy. So yeah, that's an interesting place. So let's talk noise reduction in terms of, we just showed how the feed, Wolfgang adjusted a feed to get noise reduction. Putting on a filter between the LNA and the receiver, how effective is that? Or that's the right place to put it, right?
I would think so.
You can't put a filter there. It'll kill your noise function or noise factor.
So is a filter, is it a bandwidth, say a band pass filter, so it cuts out the low and the high? Is that appropriate at all in a radio astronomy setup?
As Wolfgang did, yes.
Well, he put that as part of the feed build, right? But not a you know, a filter you put in line with the.
No, you don't want to put a cavity filter or something like that in there. That'll kill all your signal, and it'll bring the noise level up. The loss in a passive component is that same dB loss or gain in the noise factor. So it could be really bad.
Okay,
so you recommend.
But once you're behind the LNA, you are fine to put in whatever filtering you like. Before the LNA is really critical, and putting in a filter in there, maybe a low loss cavity filter, would be the very last resort in extreme RFI situations.
I'm thinking one of those bandpass filters that, you know, little chip bandpass filters you put after the LNA toward the receiver. That would be okay.
That'll be okay.
All right.
Yeah, that'll be okay.
Okay. All right. Let's see. Wendy. No mic. Nothing happening. Okay. I do want to take a quick poll of the radio astronomy formula series, and particularly the new people. What don't you know that you would want to have a quick slide set on? Description of, of a setup, of a formula or whatever that I could add on there. The goal is little 3-minute videos that explains one little particular thing. So, you build those up over time, you can actually figure out what's going on. Anybody got any ideas they want? I don't hear anybody. No. Okay. I'll just start picking the formulas and keep going the way I am. So if they're useful.
Oh, yeah, I do have a suggestion.
Okay, go ahead.
Terry and I have put together some stuff for the H1 line, but it's a little technical. In a friendly presentation of the H1 line, why it's there, and everybody can receive it with an SDR. I think for an educational set of slides or a video, yeah, that would be helpful, and certainly even for us here at LTO and the rest of us.
All right. And I do have one up there currently. Basically, it's after you receive the data, what do you do with it? But actually trying to receive it with, let's say, a scope in the box. I think that's the process of receiving it and documenting, I guess, would be a good way to do it all the way through. All right. Something to work on there. All right. Let's see. I don't have anything else for this meeting. Anybody else got anything? All right.
Just a comment. I had put this in chat. We're still looking for presenters for the SARA National or Eastern Conference in Green Bank in August. If you could possibly get abstracts or at least an email with the proposal of your topic, we'll get you on the schedule. Looking at time slots, we've still got about 6 good time slots. Conference starts on Sunday. That'll pretty much be taken by Ed Herrmann's intro to radio astronomy, and he'll be covering much of the material David just mentioned, followed by Skip Crilly and hands-on with the 40 meter. That'll pretty much take up Sunday because of the hands-on with the not 40 meter, 40-foot telescope. And Monday and Tuesday will be filled with technical presentations. We're thinking Wednesday morning will be high-tech tours and hopefully a tour of at least the ground level of the Green Bank telescope. So again, we have about 6 good time slots available. We'll be publishing your papers in a proceedings document, but PowerPoints would be appreciated sometime in early to mid-July. But for right now, if you could just email me, the email is in chat, but it is jay.wilson@v as in Victor, odec.net. Would appreciate that. Thanks.
All right. And remember, you guys can sign up on the store to either go in person or to go in Zoom. So at least if the earlier you sign up, the earlier we find out who's going, and we can make arrangements. Okay. Okay. So the next meeting is the Drake's Lounge, which is the third Sunday of the month. And then that next Friday is the Drake's Lounge Australia. and those guys are still struggling with their big dish that the bull gear that controls elevation has been stripped. So they've been offline with the big one, but they've got a lot of interfaces with Parks, which does all the pulsars, most of the pulsar work. Okay, that's all I got. Thank you very much, everybody.